Nice to meet you, everyone. My name is SungHyoun. I work at FSI in South Korea. FSI is responsible for the security of Korean financial industry. I'm researching mobile security at FSI, and I do penetration testing for Korean financial companies. I have experience speaking at several international security conferences. Today, I'm going to talk about the Android MRI interpreter for effectively analyzing apps. There are two people here. One is a doctor, and the other is a security researcher. In my opinion, these two people are doing similar things in some ways. The doctor examined the human body and find the disease, while the security researcher analyzed the application and find vulnerabilities. Ultimately, they are doing the same work of analyzing body or app and finding the problem there. However, medicine has much longer history than the computer scientists. Doctors have been studying the human body for much longer than computer scientists. If we look at the drawing from the 1600s, you can see that they performed the surgeries to examine the human body and find the disease even long ago. As time passed, in the 1900s, X-ray were developed. But in order to examine the human body in great detail, it was still necessary to use the surgical knife to directly examine the body. However, this method of using surgical knife has significant disadvantages. The body's defense mechanism have a natural resistance to cutting the body with a surgical knife. So if a doctor cut the body in that way, it can cause a shock to the body and take a long time to recover. So what about the security researcher? Do they face same challenge when analyzing apps? Unfortunately, yes, we are also similar. We are also using the knife just like them. We use the system function ptrace to forcibly access the process of the app for analysis. However, as mentioned earlier, using knife can cause a resistance due to the body's defense mechanism. Therefore, it took a long time to recover. The same is true for app analysis. Apps have their own runtime application self-protection technique. So using ptrace can cause a resistance and require more time for analysis. They do similar work and face similar challenges. But medicine, with its long history, has found a way to address those challenges. In the 1970s, there was a huge change. With the advancement of engineering, medical devices like MRI or CT were developed. People only needed to write down and do nothing. These machines were able to take a picture of a specific organ without cutting the human body with a knife. Therefore, I have decided to develop an Android MRI to discover vulnerabilities and analyzing app. It provides 3 key features like medical MRI. The first feature of this Android MRI is that it analyzes the code at the OS level. We will forcibly access the process. Android OS wrote and executed the app code using the runtime and the interpreter. So they can be used to analyze the app without being limited by the defense mechanism applied to them. Second, medical MRI provides the ability to capture image by layer, allowing for the detailed examination of a specific organ. They were not just simple photo, but rather enable precious cross-sectional imaging of organ with the human body. Therefore, I developed a feature in the Android MRI that dynamically output code image of the target function. This image allows for the very detailed examination of each instruction executed with the target function. These images include all necessary information such as function name, program counter, dalvik instruction, and the register value. And just as a doctor searches for the tumor in MRI snapshot, we can also search credential in register value output by Android MRI. Thirdly, medical MRI traces the flow of the blood used in organ and provide this information in the form of image data. We could easily see where the blood inside the human body was flowing from and to. In the field of security, there is a technique called taint analysis, which traces the flow of data. We use this information to find the vulnerability and analyze apps. Thirdly, in Android MRI, I provide the ability to trace the flow of target data and visualize it as a core graph. The red box in the graph indicates where the target was first detected, while the green box indicates where the detected target was moved, copied, or transferred. Core graph allows you to quickly and effectively see the entire flow of the target creation and use. In conclusion, in this talk, we introduce Android MRI to automatically bypass RASP without analyzing them or patching the code. Then it generates a core graph for the target data that require analysis. By using the graph, it is easy to visually understand how the target data is created and passed to the other function. And then, if we want to examine the specific function in detail, we can easily obtain the code and the data by taking an MRI snapshot. Finally, at the end of this talk, I will demonstrate how to use the Android MRI to find vulnerability and widely use the messenger in very short time. Before utilizing the Android MRI to find vulnerability or analyzing apps, let's take a look at how these things were designed. To do so, we first needed to understand in detail how an app's code is loaded and executed in the Android. While understanding this process may seem boring, but if we understand it perfectly, we will be able to control all the code and data that is executed in the app. First, let's examine the type of the code that can be executed on Android. There are three types of code. Android app files are stored as a DEX file, which are bytecode by default. However, to improve the performance for frequently used parts, they are compiled into native code, such as AOT and JIT code. DEX bytecode and AOT code are saved in file, while JIT code exists in memory as a cache code. Let's take a closer look at how these three types of code are generated and compiled. This is a slide that shows that the whole process of how apps are generated and compiled in Android. First, when you try to install the app, APK file is downloaded to your Android device along with the optimized profile data. The profile data holds information about frequently used function by previous users of the app. During the installation, the profile information is used by AOT compiler to selectively compile the bytecode in AOT code. For the functions that are commonly used by user and infrequently used code is not compiled and installed as a bytecode. Second, when you execute the app, ART check whether the code of the running method is compiled or not. If the code already compiled by JIT or AOT, it directly called the code loaded in memory and executed it immediately. If this code is still bytecode, the interpreter executed it and increased the method execution counter. Functions are classified into cold, warm, and hot state based on their execution count a function starts in the cold state, transition to the warm state as it used more, and eventually reach the hot state with even more used. So if the counter of the method continue to increase and it transition from a cold state to warm state, the profile information such as the number of method execution is saved in the device as a file. While you are not using the phone but just charging overnight, this service compile the warm method using AOT compiler and save it in the file as AOT code. Next time, the method will be executed right away as your AOT code from the beginning. And if the counter keeps increasing and finally becomes hot state, the method is compiled in the real time by JIT compiler and stored in the memory as a code cache. Then code loaded in memory is executed as soon as the function is called. As you can see here, ART has various states of code and complex structure. So multiple type of the code can be mixed and executed when app is called. As shown in the picture, one main function consists several sub-functions, and each sub-function also consists several smaller sub-functions. Let's take a look at the step to call and execute sub-function 232. Main function, sub-function 2, sub-function 23, sub-function 232 are called in that order. Each function exists partially as a bytecode and partially as a compiled code. Because of that, we need to call the compiled code from the bytecode and the bytecode from the compiled code. This cross-call from the different code make ART structure more complicated. Within ART, various types of code are called, so it is important to carefully control the execution of different types of code in the seamless sequence within ART. To gain more detailed understanding of the flow of ART, I analyzed the flow of ART using the Android source code. This is the code flow that analyzes the execution process in ART. I analyzed this structure for a long time. I think it may not be easy to understand the whole process at once, but if we focus on the code execution aspect, there are two parts in the whole picture where the code is executed. First part is compiled code. This function invoke and execute the compiled code. The second part is the bytecode. This function invoke the interpreter and execute the bytecode. Here, compiled code called the bytecode and the bytecode called the compiled code. All the information required to execution the app go across these two parts. I will try to express this structure in a simple way. In two functions, each executes the native code and the bytecode, and they call each other. Therefore, if we can examine these two functions, we will be able to know all the code being executed. But looking at the native code being executed is useless. Native code has already undergone many optimization process. So even if we examine it, it's very difficult to guess what the original code was. So I changed the flow of the code to prevent execution of native code within ART. When the request of native code execution is made, the interpreter is called to ignore it and instead invoke the bytecode. As a result of this flow change, all execution become possible only via the bytecode. As seen before, when the app is executed, the compiled code and the byte code in ART call each other to execute it. And I modify the flow of ART so that the byte code is executed instead of compiled code by changing code invocation flow of ART. In conclusion, in this modified structure, all the code of app is executed only via the interpreter. Therefore, if you can understand how to execute the code in interpreter, you may be able to create an MRI interpreter. So we will investigate how the interpreter interprets the code. The very first step is the beginning of the thread. When an application is launched in Android, it creates a first thread of execution, known as main thread. The main thread is responsible for the dispatching event to the user interface, as well as the communicating with the components from the Android UI. All Android apps use the main thread to handle UI operation. Calling long-running operation from this main thread can lead to freeze and unresponsiveness. So we can create an additional background thread to handle long-running operation while the main thread continues to handle UI update. This thread is used when the querying database or processing file from the system or over the network. So, when a thread is created, it is stored in the thread list. And this thread list is stored in the runtime object in ART. Each thread object stores various information about the thread. And among them, the manager stack object stores the code information. When a thread starts, each function information is stored sequentially in the shadow frame. That is, code information for one function is stored in the one shadow frame. The shadow frame contains information such as the name of function, the address of the code, the program counter, and the register value that will be used when the dalvik instruction is executed. In the end, the Android interpreter receives the shadow frame, and it uses the information stored in the shadow frame to execute the code. The Android interpreter uses the micro interpreter and the switch interpreter selectively based on the runtime state. But I developed the MRI interpreter by removing these two interpreters. And I plan to use the MRI interpreter to examine all dalvik instructions as well as the register value. When the shadow frame is passed to the MRI interpreter, it first uses the method info to confirm which function is needed to execute it. After using the address information stored in the code pointer, the MRI interpreter moved to the address of the code in memory. Moreover, MRI interpreter moved forward by the number of bytes specified by program counter. Next, the MRI interpreter check instruction. Dalvik instructions are already defined, and the interpreter can examine the value of the instruction to determine its type. For example, if the value 0x01, the interpreter knows that it's a move instruction. Each instruction has its own format. And the move instruction uses the K12X format. Likewise, the format of each instruction are already defined. In the case of move instruction, it utilized by K12X format, which consists of the virtual register A and virtual register B value. Each of 8 bytes specified after the instruction. Virtual register A and virtual register B are index of the variable stored in the register. Virtual register A contains the value 1 and the virtual register B contains the value 3. in the end, this means move instruction to move the value stored in the third index of the register to the first index. As a result, we use the MRI interpreter to confirm the name of the function being executed in the method info object, and then use the information stored in the code pointer and the program counter object to identify and execute the corresponding dalvik instruction. And we can also use the information stored in the register object to identify the virtual register information that will be used during instruction execution. In conclusion, we can use the MRI interpreter to output all dalvik instruction being executed in real time, as well as the register value being used at that time, and even modify them in memory if necessary. Furthermore, we have created a configuration file and enabled the MRI interpreter to report it in order to output or modify only target information. With this, we can control all information being executed. Here's we have complete the first feature of Android MRI interpreter. By simply running the app, we can immediately examine the execution information using the developed MRI interpreter. Next, I will develop the taint analysis using the MRI interpreter to trace the target data. Since we have complete control over the interpreter, we can easily trace data as it flows via the interpreter. I have listed the instruction for creating, moving, copying, and the function calling with data. An instruction is the smallest unit of the code that is executed. So if we just look at the register when the instruction on the list are being carried out, we can trace how the data go from the when it made to when it gone. There are various types of data, and the MRI interpreter can capable of tracing all type of data format. But string are the most human-friendly data format. That's why I made an MRI interpreter that traces the string data. Then let's trace the target string data in the instruction executed via the MRI interpreter. For example, if the move R0, R3 instruction is executed, we first check if this move instruction is included in the list of instructions for taint analysis. Since move is the instruction that require trace, so we examine the source register of the instruction. Then if the string of the memory address pointed by the source register, registry, match our target string, we output this information to draw the graph for our taint analysis. As a result, we were able to output the information of the function where the target data is used and draw graph. However, this was not the desired output. This graph only shows the information used in each individual function, making it difficult to examine the flow of the target data via the entire app. It was necessary to output more information about the function execution before and after the use of data. So I have decided to use the shadow frame and the manage stack again. As mentioned earlier, all information about the executed function is stored in the shadow frame, and the shadow frame is stored in the manage stack. So when the data that I target is detected in the interpreter, I print the current shadow frame, and all the shadow frame are stored in the manage stack. The manage stack includes the information, not only the currently execution function, but also about the previously execution function. Ultimately, using this information, I was able to print all ancestor function of the currently function together. Then we were able to combine the execution of individual function to create an overall flow image. This allowed to identify data within the overall flow of app, rather than just simple listing the individual function where the data was used. In conclusion, we were able to complete a call graph that can trace the target data in the overall flow of app. The red indicates where the target data was first discovered, and the green indicates where the target data is used. And this image is the call graph of the app where the target data was used relatively simply. When an app applies the code obfuscation or has more complex flow, it tends to create more complex image. However, in the process of creating a code graph, unused code is removed and merging duplicate function call to draw graph. Therefore, even if obfuscation is applied, it allows for clear and fast analysis. This makes it possible to easily identify information such as encryption and decryption function, credential data, and privacy information. Lastly, we will look at how the environment presented in this talk bypass the security mitigation applied to the app. In app with the sensitive feature, security mitigation are applied, and we refer to this as a RASP. Many security companies develop RASP, make it as a module, and sell it. Even Google provides the developer with a safety net service as an API. Then, can you bypass RASP? Yes, because the goal of RASP is not completely block the attacker, but rather to delay the time required for the attack on the client side and to annoy the attacker. So we can bypass all of these RASP. I have analyzed and bypassed numerous RASP applied to various apps, which require to as little as a few minutes and as long as a few weeks time. As mentioned earlier in this talk, I create an Android MRI bypass RASP more easily than the traditional way. Rather than analyzing app and patching the code to bypass them, I want to create an OS that automatically bypass all RASP, making me unaware of whether RASP was applied or not. Here are two environments. One is the using tool like MagicSU to root and then analyze the app with a hooking tool like Frida or IDA. The other one is the MRI interpreter. Which of these two environments would be more advantageous for bypassing RASP? RASP detects many aspects of the OS. So after rooting and using the debugger or hooking tool can be easily detected by RASP. Then is Android MRI not detectable? No. RASP detects the custom ROM, and the Android MRI was developed custom ROM. So how is the Android MRI different from the existing custom ROM? There are already many custom ROMs, and the sensitive apps may are not working on them. Most custom ROM are created by adding a desired feature to AOSP. Custom ROMs created in this way have difference from the stock ROM provided by manufacturer. Even if you building the custom ROM without any modification to the AOSP source code, it is not the same as your existing stock ROM. So instead of using develop the custom ROM directly, I only replace the specific module I developed in the stock ROM as a base. Since RASP depends on the kernel info as a user WAN app permission module. So I stopped fighting in the user WAN. I developed the most feature in the kernel WAN. The required feature is developed as a backdoor in the kernel. And before sending to the user WAN, some data was modified in the kernel to prevent RASP detection. Due to the time constraints, I cannot explain the all apply to the technique, so I will provide a few examples to technique using this OS. This is the booting process of Android. Android device implements the secure boot via the chain of trust. The first primary bootloader verifies the signature of the next one. Next bootloader verify the one until the Android bootloader. The Android bootloader will verify and load the kernel if the OEM unlock menu is disabled. If the OEM unlock menu is enabled, the Android bootloader immediately load the kernel without verification. The stock kernel is signed with the manufacturer's private key. But the kernel we have created is not signed by manufacturer private key. Therefore, OEM unlock enable process is required to change the custom kernel. So Google allow use custom ROM for developer using the OEM unlock menu. However, when this feature is exploited, an attacker can physically modify the kernel of the normal user. So Google is presenting the color about the boot time according to the device state. As you can see, it is displayed green, yellow, red, or orange, depending on the state. In my case, I have enabled the OEM unlock, and it's an orange color when booting. So I needed to change the boot color because the RASP and the SafetyNet check this. How can find the boot information in the user WAN? In AUSP source code, the init process gets the device information from pros command line and store various device information. What information in this command line? There is a lot of information about the device. Did you find it? Verified boot state information here. The OS wrote this information and stored. And that information was used by RASP and SafetyNet. So where does this information appear in the kernel? If you call the pros command line to check the boot status of the device in the user WAN, you can see that the string saved command line is output. So I changed the orange of verified boot state to green in the saved command line string. I did it this way 4 years ago. Now I have patched the entire content. I get the command line information from the stock ROM and hard-coded it into my custom kernel. As a result, the information passed to the user WAN is the same as the stock ROM command line. In this way, I modified some data that kernel level to prevent RASP detection. I am currently fighting with the advantage by minimizing change of the OS and patching most of the information in kernel. The second example is the developing a privilege escalation backdoor by patching the kernel. Developing an exploit to root on the stock phone is not easy, but creating the privilege escalation backdoor by modifying the kernel is much easy. I decided to use existing module being in Android system for privilege escalation. The system bin directory contains the default command such as copy, share, remove, and mount. I thought I could make a backdoor from the default command without binary patch in the user WAN. when I executed the sh command in the shell, I wanted to obtain the root permission. I am modifying the kernel code of handle this part. As you can see the code in the kernel, if we run the sh command in the Android shell, the kernel executed the execv function. So I added the code to this part, and then verify that the sh command is executed in the shell. Then I create a root credential, and the UID and group ID values are root credential are all assigned as a 0. In conclusion, I was able to get the root process by simply invoke the sh command in the shell. This technique is very simple and lightweight, but this technique is difficult to detect by RASP. Even if the RASP knows this technique, you will be able to bypass this by adding the sh command option that only you know the password. Now let's take a look at the demo of the analyzing WhatsApp using the Android MRI. The analysis target is the most widely used WhatsApp messenger worldwide, and we will analyze two features. On the website introducing WhatsApp, two security features are explained. One is a two-step verification, is an optional feature that adds more security to your WhatsApp account. When enable this feature, you create and confirm a unique PIN that requires to access your account. And if you reinstall WhatsApp after SMS verification, you will be requested to enter 6-digit PIN. Therefore, you should not expose this information to others. The other feature is end-to-end encryption when exchange message between the user. Of course, WhatsApp also restrict itself from the running of the rooted environment or custom ROM. However, we can analyze without being aware of this restriction. In this OS, it was bypassed automatically. Okay, let's look at the demo. Launch WhatsApp and go to two-step verification menu. Setting and account. And you can see the two-step verification menu. First, before registering PIN, two-step menu, I will closing the app. This app is the terminate background WhatsApp process. Before registering the PIN two-step menu, I will set the PIN in the config file for trace. First, I connect a mobile phone. I get the shell privilege. This is a normal shell file, sh file. This is a normal sh file. This sh command is original. It's not modified. I have received the root privilege in the kernel. Then open the config file. I move data local temp, and I open the config file using BizBox. In config file, you can set the target app UID, set string, and set include and exclude target function. First, we need to get WhatsApp UID. data system packages list contain the app's UID. I search watch app. You can see watch app UID 10250. Set UID 10250. Trace mode 2 and register and search item register 135246 in search item. 135246 in search item. 135246 is a PIN number to register in watch app. Start print log and restart watch app. Registered PIN are not open yet. Go two-step verification menu. And turn on. Insert 135246. You can see that instruction and the register value in the real time. Print the function name, instruction, and the register value of 135246. You can see very easily. Close and restart watch app. Close watch app. And I restart watch app. The pin is detected again. Watch app request input pin. The pin is detected again. Watch app request input pin. And the pin is detected again. Close and restart watch app. This time, it does not ask for the pin input, but the pin is detected again. Every time you run the app, the pin is detected somewhere. Go to two-step verification menu. And turn off the two-step verification. Close watch app. And restart watch app. No pins are detected this time. And I try to register new pin again. New pin is 778988. 778988. And close watch app. And open the config file. change mode 3. Mode 3 is the graph mode. We can see the core graph. Mode 3 is the draw graph for target string. Set search item 774988. Save compute file. And clear log. I output the log as a log file, graph log. Restart WhatsApp. You can see the draw data. And using this information, I make a call graph. Change the first found part to red and delete duplicate. And set the graph format and generate a graph. Look at the graph. It is easy to see how the pin were detected. If we look at the zoom in, you can check that the pin was decrypted using the Android default decryption function when starting the app. If you are looking close at the x.0pg A02 function, you can copy the function name and register it in config file. Trace mode 1 is all trace mode. And target function is x.0pg A02. And the restart tab. You can check the all information about the function. I have already analysis that the pin is decrypted in shared preference every time app is started. And if you don't set the include function, you can see all function information being executed. I don't think this is a critical vulnerability. It's just a credential weak when the pin is unnecessarily exposed in the memory. I just wanted to let you know that you can easily and quickly analyze the app using the MRI interpreter. Thank you for listening. Thank you.
Thank you, SungHyoun. Now we go to the Q&A. Is there any questions from the audience, from the floor? Yes, one.
Sorry, my English is not good, so you can ask a question simply and slowly, please.
Yeah, sure. Great talk. I really like it. I'm just wondering, as a developer, is there any way that I can pass encrypted string without using so that your tool can't trace my encrypted string?
Sorry?
Hold on, let me just... Is there any way that I can pass an encrypted string without your tool tracing
source code? Next year, I release the open source, but not yet.
Okay. Is there any way that I can pass an encrypted string without being traced by your tool?
Sorry, I can't understand.
Yeah, it's okay. I'll come to you later.
질문이 지금 패스워드가 지금 메모리상에 노출이 되어 있었는데 메모리상에 패스워드가 노출되지 않고 앱을 개발하는 방법이라든가 그런 부분에 대해서 혹시
Sorry, if you use the credential in the app, then you rewrite the memory address. You use the string. You cannot string. String is always remain the memory. So you can use the byte array or pointer, and then you use the credential and rewrite that address.
Thanks.
Thanks. Any other questions? No? Okay, one more round of applause for take a picture of your app code and your MRI interpreter.